The topic of today's talk and the talk that will be tomorrow would be the new approach for functional integral. Let me remind you that previously we studied functional integral of the following form. Sorry. And here it was important that space of fields X had linear structure. It determined the measure. And here important was concept of sum. Depends on linear structure. However, in classical mechanics, action could be something like this. It's square of velocity. On some manifold X. Without any linear structure. So X could be something like a sphere, or something even more complicated. How to do functional integral in this case? And in similar cases. The idea is the following. Understand S as critical values of I'd like to put J here. Second, study integral. Integrals like consider here this thing as a perturbation and observe that integral dp exponential I pj dxj over dt is delta function. And solutions to equation or generalize. So star is what I'm going to get at the end. And I will get there in several steps. Step 1. Mosaic William in representation for delta function. Step 2. Understand correlators. Okay, I will not say write correlators. Functional integral of x at t1, x at tk, p at tau 1, p at tau k, true, finite dimensional integrals. over so-called instantons. It's called instantonic theories. Of Frankel, Nekrasov, and me. Okay? Step 3. Take it as a definition. Definition of a functional integral. I would call it mathematical definition. So today and tomorrow we will go along these steps. Step 1. X is a space. Omega 1, omega k are differential forms on X. I will write them as a function of X and psi. Like omega G1 GP, psi G1, psi GP. Let N be a space of zeros of functions Fa. We will assume that N is finite dimensional. How to write? Integral over N of omega 1, omega k in terms of integral over X. Idea. It would not be an integral over X. over some supermanifold. They'll call Y. That is roughly E times X. E is the space of equations. E shifted by 1 means that it is an odd space. With coordinates. So how did I denote the function? FA, pi A, odd. Explicit formula. Integral over n of omega 1 omega k is integral over d pi a dpa. Idea of the proof. I call it Matai-Quillen integral. Consider exponential. Minus epsilon by I by B some GAB. Take integral over PA fields, variables. They are not fields yet. Get GAB. So it's inverse metric. Look at something distributed along zeros of FA. So here it's the number of equation. Now the integral let me call it double star. It's approximately this. Plus epsilon corrections that go to zero when epsilon goes to zero. Example. M equals to 1. Omega 1, some function f of x. A also equals to 1. Integral that I'm going to take is like this. Sorry, I have already taken integral over p. Now I take integral over psi and over pi. I forgot the square root of epsilon. Now, how to compute this integral? Suppose that f of x0, I called it y. Then what do I have here?
I'm sorry, I didn't quite catch that. We are supposing that f is 0, or f is 0 at some point y?
If at point y is 0.
Oh, okay.
Y is 0 of f. So here I'm taking the Gaussian integral. I get square root of epsilon 1 over f prime of y from the Gaussian integral. I also had this square root of epsilon that I forgot here. I have f of y, f prime of y, plus O of epsilon terms. It gives me f of y. So it's a very simple exercise in Gaussian integrals. Maybe I went too fast. If I went too fast, then please ask me questions. Okay, since no questions, it means that I went with the proper speed. So now I have the following formula. And now look, I'm going to read this formula backwards. I'm going to use this formula as a definition of the right-hand side. In future, x would be infinite dimensional, E1. Would also be infinite dimensional, while n will still be finite dimensional. And then it would be a definition. Important development of the idea. If I use this as a definition, I know how to integrate differential forms, namely functions of x and psi. However, in the integral, I also have objects like p and pi. How to get so it's my equation. And probably I'd like to get pi a here, or say pb. How to get it? There is a trick. Consider family of functions. What kind of family? I would like to call parameter here. There is no good name. L. Okay, it's also a function. Then with no pi b is just what? And here I have omega 1, omega n. So it is just the derivative with respect to LA of the
I'm sorry, what does it mean with no pi b?
Suppose I am not inserting pi b.
But how does this insertion work? What is the integral that is next to the question mark? Is it like the regular one or
okay. Suppose I want to study this integral.
where PA is multiplied with all the omegas?
Yes.
Uh-huh.
So idea is to write it down like this.
Then where is PA at the bottom?
You see, that's what I'm doing. So I can get PA by taking derivative with respect to L of FAL.
Ah, all right.
So in order to get PA, I need to go to NL, set of zero of functions F, A, L. We will call NL deformed instantons. And what is interesting? It is interesting that I still have a finite dimensional integral. Remember, I assumed that the space N is finite dimensional. So I obtained integral with insertions of field P like this. Now you may also ask how to insert pi. So it seems that I need something like a source for pi. Okay. So to do this, I need to recall the scientific meaning of p plus pi. We have a the RAM differential psi d over dx plus p d over d pi on e1 of x. And what is an exponent? And what is an exponent is nothing but let me call it q. Q applied to pi a I pi a f a. So I'll repeat. Now, I would like to do the same thing for family. So it's not good to make changes in nodes. So now I promote u to psi d over dx plus p over d pi plus lambda d over dl. Okay. Introducing odd coordinate on family of instantons. So now q tilde L plus an extra p. Okay. Okay, let me write it down in scientific way. I think it's something like this. I am afraid I have too many summons. dfl over d Okay, so I have a place. So now, if f a l is fa plus la, then this expression is pa, fa plus pa sorry, plus pa la plus pi a lambda a. Okay? So we see that exponential, our old exponential, omega 1, omega n integral pi a is nothing but the derivative with respect to lambda a of what? Of the integral over n lambda L lambda of omega 1 omega n. Once again, I turned would be infinite dimensional integral into derivative of the finite dimensional integral over n lambda L. Okay, so it is a trick. And I have a feeling that I am coming to the break. Okay, why I'm writing it? After the break, I'll apply this trick to defining infinite dimensional integrals over the curved space. Tim, is it clear what the trick was?
So just differentiation with respect to what stands in the exponent, but in a careful manner, right?
So the trick is the following. To get p and pi correlator or integrals, we just take derivatives with respect to parameters of the moduli space. what would be important and what we would see is the following. We will have infinite dimensional space of fields. Okay? Then the question is, how could it be that correlators, there are infinitely many interesting correlators. How could it be that correlators could be contained in the finite dimensional integral? And the answer is, we would consider infinite dimensional family of finite dimensional integrals. And then answers would be nothing but derivatives along the infinite dimensional family. But it is good, because in mathematics, I can always consider infinite dimensional family if I'm not integrating over it. Okay? So I am back to my plan. So step 1 was Matai-Quillen representation for the delta function that I would like to do from the right to the left. So now I would like to study step 2. I would like to see functional integral as an integral over the infinite dimensional space. And get it from the finite dimensional integrals. Okay? Consider manifold Y. And manifold X as a space of maps. It's infinite dimensional. Now consider equations. Dy over dt equal Vi of y of t. So for this to be an equation, I need to do the following. So this would be FAs. Space of solutions trajectories of vector field into the space N. Note that N is isomorphic to what? Tim, do you have an idea about what is isomorphic to the space of trajectory?
Maybe y factored by
Just why?
something? Just wait.
Why? Because trajectory starts somewhere.
Ah, all right. Yeah. Ah, it's
So it is
trajectories, not orbits.
no trajectories, parameterized trajectory. Okay? So we have a finite dimensional space. Now, we would like to consider the following integral. dy d psi dp d pi functional integral over what? Of what? And here I need to put an exponent. The AFA, of course, goes to the integral. P of t I j dyj over dt dt. That's first piece. And there is the second piece. And here I have vector field. So this is what we call bosonic piece. And there is also a pi term, a pi piece. Minus pi j dvj over dyk psi k dt. So this is what we have an exponent. And we have some differential functions in the predexponent. Omega 1 of y at t1, psi at t1, omega n, y at tn, psi at tn. So this is a simple case. No p or pi insertions. then the good question is what we will get. We will get something. It may be computed. As follows. Let gamma of t be the trajectory starting at y0, okay? Gamma j of 0 is y0j, okay? Then this integral is, of course, finite dimensional integral over y0, and I integrate over y. And what I have here, of course, I'm integrating over y0 and over psi0. And I need to insert in the omega gamma j of t. And what do I need to insert for psi? So you may easily check that for psi, I should insert what? D gamma j over d y0 k psi 0 k, etc. omega n. This thing has a known mathematical meaning. It's called pullback of the evaluation of omega 1 at point t1 note that sum of degrees of omega should be equal to what? To dimension of y. So if I would like to compute it, I need to compute trajectories and consider these evaluations. Now, in general, it is hard to compute trajectories, right? So I go to example. So this example is particular in the sense that I can compute trajectories explicitly. It's not a conceptual simplification. It's just technical simplification that I am able to write down explicit formula. Let y be r. Let n, say, be equal to to 2. So I need to pick up omega 1. Let it be delta form of y minus I don't know what to put. y1. Let omega 2 be just some function of y. It's an example. Okay? And also let, you see, I'm going to compute trajectory. Let me take v be equal constant. Okay? v naught constant. Then I can compute trajectories. So delta function has this dy. So gamma of t, and it also depends on y naught, equals y naught plus pv naught. Okay? Now my computation is the following integral. Here I have delta of y naught plus tv naught minus y1. Now instead of dy, so what I'm putting instead of dy, I'm putting the derivative of the trajectory with respect to y naught. So it's just psi naught. And then I put f, and this happens at moment t1. And here I put this thing at moment t2. And I integrate. And the result is pretty obvious. I integrate delta function, so I know that y naught is y1 minus t1 v naught. And I plug it here to get f y1 plus t2 minus t1 v naught. So this is the result of the computation. Okay? It is that easy. And you may see that result depends on, okay, now, result depends on T2 and T1 if V naught is not equal to 0. So you give me function f, I computed the correlator. Now I want to study so-called P observables. So how do I do it? I study a family. Last time I was supposed to study this. Well, I will study let me call it V, and let me call it U. It would correspond to an observable Pj Uj of U plus pi j duj over dyk psi k. Let me call it OU. Okay? Now I know how to correlate. Now I know how to compute. Correlator of OU at point tau omega 1 T1 omega n Tn. It's of course what? I want to put it. I made a mistake. I want to put it at a very particular point. T minus tau. This would correspond to observable. So it is d over dl. Of course, when l equals to 0. And here I compute an integral over space and L. And here I have evaluation at point T1 of omega 1 times evaluation at point Tn omega n. I would put here 3 lines saying that this is a definition. So gamma L is solution to the following equation. Okay, so this was too abstract. Let us come to example. We have our favorite example. Y is R. Let us even simplify our life. Maybe not. Okay. Vj of y would be v naught. Uj of u would be just u, okay? Also constant. Now it's interesting to solve this trajectory. It is easier to draw them. So here is t. We start at y naught. Then we go like this. Up to the point tau. And then what happens in the point tau? At the point tau, we have a jump. And then we continue with the same speed. So what is the value of this jump?
UL.
Of course. So this is the explicit description of gamma L trajectory. Okay? Now let us do the same computation. Let me even simplify things a bit. You see here, y0 was y1 minus t1 v naught. For simplicity. Take t1 equal to 0. So trajectory will start at y1. Remember that we study delta function of y minus y1 at point 0. Function at point t2. And now new observable of u at point tau. So this is expected to be d over dl of what? Value of the function at trajectory gamma L at point tau 2. Okay? So now I need to take my trajectory inside this equation. And I have two cases. Case 1, T2 is smaller than tau. Then the result is just d over dl of what? Of f y1 plus t2 v naught. So what do we see? We see no dependence on L. Okay? So it is 0. Second, T2 is greater than tau. So jump already happened. Okay? Then we are computing this. Plus team knows the jump. It is U times L. Okay? But now we may compute it. So I think we can differentiate. And the answer is df over dy at what point? Times u. So we have a jump. Now the value of this jump depends on f. Let us take, for simplicity, f of y. So what f of y, Tim, would you propose? For simplicity. So constant is not an interesting. Then there is no jump.
Well, we can try linear.
Yes. And then it would be just U. So correlator, we have this delta. We have y of t. Sorry, y of t2. And we have OU at tau. As a jump. Value of this jump is U. Now let us see. The value of a jump is independent of V naught in this particular case. But probably we can say something about the jump in general case. Jump in correlator delta F of T2 of U is what? Is surprisingly correlator of df over dy at point T2, as we may see from the formula for star. Times U. So what did we obtain? We may compare result with functorial. Definition of quantum mechanics. What is the language? What is the dictionary? First, space of states. There would be differential forms on Y. Second, Hamiltonian. LV naught. Lie derivative. Observable. Observable F. Operator even omega. Sorry. Observable omega, operator of multiplication by omega. Observable OU. Lie derivative. LU. Correlator. So it is a tricky thing. We have initial state, psi 0. Then we have evolution with the Lie derivative, LV naught. Then we have observable. So what was the observable that we put there? There are two cases. First case was where T2 was smaller than tau. So we go all the way to T2. Then we have this F. Okay, well, let me do it as follows. Let me draw you the universal formula. All the way up to CT. So these are correlators. In factorial approach. So statement. Instantonic approach. Instantonic approach. reproduces functorial approach. On curved y. I have not proven this, but I can illustrate this. The value of the jump in functorial approach is obviously
There's a question in the chat.
thank you. Let me see. Is a commutator of 102. So exponential of the derivative is the flow along the vector field. That we observed. So once again, it is a subtle issue. So I would like to continue it next time. Okay? And next time would be tomorrow. So tomorrow we will continue the correspondence between functorial approach and instantonic approach. So summarizing, today I explained the multi-equivalent integral. First thing, I explained multi-equivalent integral for families and how p and pi fields appear. And I already applied it to quantum mechanics. So I did a lot. So see you tomorrow.